Welcome back. We are going to talk about the properties of elasticity in this lesson, and these are going to be our learning outcome. We are going to explain the meaning of the terms limits of proportionality and elastic limits. We also have to talk about yield points and fracture or breaking points. Then we will try to describe what is meant by ductility and the brittle properties of material. Later on, we'll be using the extension force graphs to determine the limits of proportionality and elastic limits of material. So you should be able to identify these properties when you are given an extension force graphs. Before we continue with that, let's try to review what we've learned so far. We said that materials can behave elastically. And what do we mean by elastic? We can apply forces to the material to deform them, and if we leave the material, it will return back to its original shape. A material like that is said to behave elastically. It is elastic behavior. Now, for some materials, within their elastic behavior, they will obey what we call the Hooke's law. That will mean that the force that will apply to the material will determine how much it will extend. And it is so linear that you can predict, having a given force, you can predict how much the material can extend. And the Hooke's law will only be true or will be obeyed if the force is small. If we keep on increasing the force, the material tends to defy Hooke's law and the elastic property. It then tends to behave plastically. We talked about the plastic behavior of material. So somebody may ask, if we keep on stretching the material so that it exceeds or it goes beyond the elastic behavior and goes to the plastic behavior, we keep on stretching the material, what will happen next? That's what we are going to talk about. We are going to use this graph to explain some key milestones in that stretching. Let me emphasize that there are some definitive terms when it comes to elasticity. Here you can see stress and we can see strain. We don't want to complicate things. You can find the meaning of stress, you can find the meaning of strain for yourself, but I want to say that stress is much related to the force that is applied to the material. Indeed, it is the force per unit area that is applied. So for now, let's take it that the stress here represents the force that is applied to the material. Similarly, the strain is the extension divided by the original length. That will be the strain. If you apply force to a material, it extends. How much it extends divided by the original length is what we call the strain. So for now, we don't want to worry ourselves so much. Let's take strain to be the extension, and let's move on to interpret this graph. Now we start applying small forces. I told you stress is force, so we start applying small forces and ignore this part. We are not going to go into details or the key points. Ignore this part. So it will be stretching linearly according to the stress, and that will be the region where we have the material behaving elastically and obeying the Hooke's law. Listen again. This part, we can see the material obeying the Hooke's law, and it is also behaving elastic. Thus, if we apply a force up to this point and release the force, the material will return back to its original shape. If we stretch it further, where is the mouse? to this point, it is still within the elastic region. So this force will still maintain the material in its elastic behavior. So it will return back to its original shape. But there is a point that we call the proportional limit or proportionality limit. From beyond that point, that's when we increase the force beyond that point, the material will no longer obey Hooke's law. If we were to predict according to Hooke's law, then the material will stretch up to this point. See the tip of the mouse. Yeah. But here we are, it has deviated slightly towards the right. So it is no longer obeying Hooke's law. But remember, between the proportional limits, where is the mouse? Yes. From the proportional limit to another point which we call the elastic limit, the material is still behaving elastically, but it is not obeying Hooke's law. This is what I mean by saying that some materials can behave elastically while not obeying Hooke's law. So here is a case that we have a region where the material is elastic but it's not obeying Hooke's law. Alright. If we keep on increasing the force, then the material will now deform permanently. That's if we stretch it beyond this point, the material will no longer be able to regain its original shape. It will now become plastic. That's you stretch it, and wherever you stretch it to, it remains there. So we have a point we call the elastic limit, and that limit, if we exceed it, the material will be deformed permanently, and that's what we call the plastic. So from here onwards, the material will behave plastically until it breaks. There is a yield point here, and it is, let's take it that it is the elastic limit, because the yield point is the point beyond which the material behaves elastically. So it is more or less the elastic limit. So let's keep that point. So if we keep on stretching the material, there will be a point where the material will now rupture. There will be a failure, or we can call it a break. It will break altogether. Alright. So this is how a material behaves if we keep on stretching it, applying force and stretching it and stretching it. This is how it behaves. In general, there could be several different ways, different behavior, and different things in other things, but this is enough for you to write your exams or to teach in the JHS. Now let's look at another important feature about the stress-strain graph, or the force extension graph. There are these terms that we can use to describe materials: brittle, and then how do we call it? Ductile. Yes. We say a material is brittle if it breaks with little or no plastic deformation. Thus, if a force within the elastic region or just beyond the elastic region causes the material to break, then we say the material is brittle. That's enchelebu. So, elastic akrana is elastic limits. Now, a breaking. That means that there is little or no plastic deformation. And plastic answer a breaking. A elastic limit na a breaking. You see, in that case, we say the material is brittle. On the other hand, if we can stretch the material to behave plastic for a very long force, or for a very great force, or for a long strain, then we say the material is ductile. It is ductile. Okay, let's have a look at this stress-strain diagram. The stress and the strain could be qualified with tensor. The tensor is just a force that is opposite to each other and applied on an object. So if I stretch a wire, then the force I use to stretch it is simply called tensor force. we are not going so much into it. Those of you who are enthused can read more about tensor and then the stress. We are assuming this side is the force and this side is the extension. I told you the strain is simply the extension. Let's understand that way. Then we'll move on. There are three materials labeled A, B, C, D, drawn on a force extension graph. The materials are behaving differently with different force applied to them. So let's try to describe how the materials are behaving, and we will answer some questions on these materials later on. Now let's take the A. A is behaving elastically and is obeying the Hooke's law until this point. So when we apply this force to it, A will break at this force. Now by the time we apply this force to it, it would have extended just a little. You see, this is just the extension. So A doesn't extend for long. But with this force, A will break. So think about it. Is A brittle or it is ductile? Let's move on to B. Now B will obey Hooke's law. It will be elastic until it gets to the point P. P is called the limit of proportionality. Thus, it will obey Hooke's law until this point. Beyond it, it will no longer obey Hooke's law, but it will still be elastic until it gets to the yield point. I told you the yield point and the elastic limits are almost the same thing. Just on infused materials, that they will separate the yield point and the elastic limits. So the yield point is here. That means this is the point for elastic limits. So it will behave elastically while not obeying Hooke's law until this point. Then afterwards, it will behave plastically. It will have a plastic behavior until it breaks at this extension. Still short extension. You can see that. But it's longer than for the material A. Okay, let's look at the material C. The material C behaves very well elastically. It will behave elastically and obey Hooke's law until it gets to this point P. But we can still stretch it even beyond the elastic. The elastic limit is not indicated, but we assume this side will be the plastic behavior. So it will behave plastic behavior. It will have the plastic behavior until it gets to the point C. It gets to this point. By that time, it would have stretched a lot. This one is the extension, so at this point, it would have stretched a lot before it breaks. So think about it. Is it ductile or brittle? Compare it to A and B. Let's look at the last one. The last one, would you say this is a linear part? It's difficult to say so. But if you come close to the 0 point, maybe the point of linear part is very, very short. Yet this material will have plastic behavior for a long stretch before it breaks. Even at the time it breaks, the force that will be applied is very low. Is that okay? This is the force axis. The force applied to it is very, very low. So think about it. Is D a ductile material or a brittle material? Okay. Now let's move on to our examples. Example 1. I want you to arrange the material in order of ductility. In order of ductility. You can start talking about the increasing order of ductility or the decreasing order of ductility. So if ductile, a material is said to be ductile if it has a long stretch before it breaks, then D is going to be more ductile and A is going to be the least ductile. A is going to be the least ductile and D is going to be the most ductile material amongst the three. Arrange the B and C for yourself. Now example 2. Which material needs the greatest force before it breaks? Which material needs the greatest force before it breaks? Now, you simply have to look at the breakpoints of each material, and at each point, look at the force that will break it. So for D, look at the force that will break it. Is this small or great? For C, look at the breakpoint and read the force that will break it. Indeed, you may have to increase the force to some point and then reduce it before it breaks. Okay? Alright. So let's say the maximum force that will be needed for this one will be up here. And then for this one also, the maximum force that will be needed to break it will be somewhere here. Then A, when we come to A, the maximum force that will be needed to break it will be somewhere here. So which material needs the greatest force before it breaks? Think about it.